All right, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here, hit the notification below, and you'll get notifications for this series and a bunch of others on our channel. We're doing multivariable calculus. We're in chapter 3, which is vector calculus. 3.2 is going to be line integrals. Specifically, we're going to do line integrals of functions of 2 and 3 variables. Let's do that. Okay, for line integrals over the plane, we're going to have a function of 2 variables. What we're going to do is we're going to have some arbitrary curve C, and we draw it specifically so that it fails the vertical line test, so it can be arbitrary. It doesn't have to be the graph of a single function anymore. We've got some horrible curve. What we had to do in the previous classes, hopefully, and this is what's going to be hard if you don't remember from a previous class, we didn't have time, but you need to know how to do parameterization of curves. And then we're going to do line integrals over those parameterized curves. Instead of viewing that as a function, we can't partition the x-axis into a nice sub-interval. So what we do is we take an interval AB in our parameter t and chop that up into sub-equal intervals. Then in each of those, we're going to see that we're going to get a delta SI, which is going to be the sub-arc length of that curve. And then we're also going to push this derivation from arc length. This ds is the arc length differential. Putting this all together, what does that say? We have a function of 2 variables. We chop up the parameters interval into sub-intervals. And then in each one we get a sub-arc length. Then we're going to define the line integral of f over c as this limit of Riemann sums. But the limit now is the sum of f of xi star yi star times this sub-arc length. And that's what we're going to now have to figure out. What is this ds guy, so that we can actually compute with these things. What that says is this ds guy is going to be this guy, and we can put it all together. And long story short, that's the only thing you want. I'm going to guess at first, how do I compute a line integral? And this is how we're going to compute. And I have a much nicer vector form for this. So let's squish linear algebra back into calculus, and we'll get a much more compact version of this. Okay, so another way to view this is if we use linear algebra now, we parameterize with a vector function of t. And then the derivative of that is dx dt, dy dt, it turns out. And then the norm of that is this guy, which is exactly that part of our differential. So the differential ds is actually the norm of r prime of t dt. That's what the differential, the arc length differential. Wait a second, because yeah, there's 2 other differentials. There's also dx, which is dx dt dt, and dy, which is dy dt dt. Or we use Newton's notation, but you'll see anyways. What we're going to do with these is we're going to replace in a second the arc length differential with these other differentials. Everyone's used to these ones in Newton's notation. Those are the differentials. Remember when we did this, du is f prime of x dx differentials. So then we're going to replace the arc length differential right away with these differentials dx and dy. Let's do an example of this. Example 1 wants us to compute the line integral of y ds, where c is the part of the parabola x equals y squared for y between 0 and 2. The first thing you have to do, remember these are going to be difficult at first. The first step is they're pushing this to a class that you already took and saying you know how to parameterize curves, right? Let's do that. What I'm going to do is c is when I have the regular Cartesian one, we have to now view each of these guys as a function of t, instead of defining y as a function of x or x as a function of y, which is what we have. We have to turn that expression into this kind of parameterization. And the best way to do that is if I write x equals t squared and y is t. I just set y equal to the parameter, and then because x is y squared, it's going to be t squared. And what does that say? Then I know that t is also between 0 and 2 because y is equal to t. A better way to do that is what I just pointed out. That says I have t squared t as my parameterization. What do I do with that? From this now, I can get the derivative is equal to 2t comma 1. And then this says that the norm of r prime of t is equal to the square root of 2t squared plus 1 squared, which is the square root of 4t squared plus 1. And then what do I need? I need f of r of t, which is equal to t, because this was y of t. We only had y. There's no x's in our expression. So we put all the expressions for x and y into the function of x. This is our function. Given all that information now, we can start computing the integral now. The line integral over c, which is this curve of y ds, is equal to the integral from our bounds a to b, 0 to 2, of f of r of t, which is just t this time, times our differential ds, which is the square root of 4t squared plus 1 dt. I know, after you get rid of all the horrible notation, this is a single integral with respect to t. And what is that going to say? I'm going to use a change of variable for a single function, which we call substitution rule. U is going to be, that change of variable is going to be 4t squared plus 1. That says 1 over 8 du is t dt, which I have, my differential. That also says when u is, or when t is 0, u is 1. And when t is 2, u is 16 plus 1, which is 17. Oh, 17 root 17. Gross. Now we're going to change the bounds. This is equal to the integral from 1 to 17 of 1/8 u to the 1/2 du, which is equal to 1 over 8 2/3 u to the 3 over 2 evaluated from 1 to 17, which is cancel cancel, 1 over 12, 17 root 17 minus 1. All right, on top of this, wait till you see how many different expressions we have for line integrals. First, we had the line integral with the arc length differential. Then we showed you that we can make that differential look compactly using linear algebra. So like, there's already two notations you had. I don't like what you're doing here. And then now we've switched it from, we've changed the differential ds, which is the square root of the square of those derivatives, to just remember that dx is x prime of t dt. And dy is y prime of t dt, and that's where that differential is coming from. So everything else is the same. You evaluate f at your parameter t, and then you go from your bounds the same, but instead of using the differential, the arc length differential ds, we're going to use dx or dy, and these are the expressions. Let's do an example with these ones. 1, 2, 3. 1, 2, 3. Oh, that was like. All right. Example 2, compute the line integral with not the arc length differential. Now we're going to compute the line integral over this curve c of sine x with the differential dx. This is not the integral from 1 to 3 of sine x dx. This is the Riemann sum. This is the Riemann integral. We're now doing this guy. It's not the same guy. What does it look like? We're going to do it over this curve, not the x-axis, not the curve y equals 0. What do we get? First, I need to parameterize this. Again, they've given it like this, so I'm probably going to say x is t to the 4, y is t, and then t is going from -1 to 1. Oh, so that would have been the integral -1 to 1 of sine x dx. But there's going to be something else in there that we're going to have to compute, the differential. This is not the Riemann integral is my point. This is not the Riemann integral. This is the line integral of sine x dx. Once I have my parameterization, what I need is all this. I need this time is my differential dx. That is x prime of t dt, which is equal to, in our case, 4t cubed dt. So it's even better. I don't have to do a big arc length differential. So that's nicer, even though we've given 2 more notations for you. Now what do? The line integral over c of sine x dx is now equal to the integral from -1 to 1 of sine of x times my differential, which is awfully convenient. And then so what does that say? That's Pavlovian, but this equals, why can I say this? Sine of 4t is going to be, here I'll just compute, and then we'll see. See, it's 0. Try to use logic instead of rough computation to see this. But what I'm going to do is, what I see is, let's let u equal t to the 4, then du equals 4t to the 3 dt. When t equals negative 1, u equals negative 1 to the 4, which is 1. And then when t is 1, u also equals 1 to the 4, which is 1. So I'm going to get the integral from 1 to 1 of, what am I going to get? Sine u du, which is equal to 0. Now what we're going to do is line integrals for functions of 3 variables. What we're going to do is quickly just give you the analogous formula for functions of 3 variables, and then we'll compute these examples in the next video. Let's do that. All right, line integrals for space. Quickly, it's the same thing, but different. Same but different, my favorite saying. How can it be the same and different? This is an oxymoron. But the only difference is we have one more coordinate, z. Therefore, our parameterization of our curve is going to be this vector function of t. The derivative of that is x prime, y prime, z prime. The norm of that is this hot mess. We put that all together, and phrasing this for a line integral of a function of 3 variables is exactly the same expression. We have one more coordinate, or if you like this one, the really nasty one, the line integral is the integral from a to b of f of x of t, y of t, z of t times the differential of the square root of the sum of the square of the derivative squared dt. Let's do one more example, and then we'll end this video. You can come in here. Let's do one more. All right, one more. Willa's messing with stuff in the background anyways. We put her in one more time, right, Willa? I know you're shy. We're going to evaluate this line integral for a function of 3 variables with the arc length differential ds, where the curve is the circular helix with parameterization, this vector function from 0 to 2 pi. What does that look like? Okay, you go run. We're going to have, for convenience, I'm going to swap those just for now because it was harder to draw the other way when I tried it. We're going to go from here, and then we're going to go over, and then we're technically going to go behind, and then it's going to helix. What's happening is we have, this is the circle in the xy plane, and then as z goes up, it's going to wind like a helix. And then we actually have, in our DNA, double helix. And then that's what our DNA is. So we're going to do a line integral over a single helix, not a double helix. What is that going to look like? I have my parameterization already nice. So C is expressed as R, which is cos t sine t t. Can you see it? Can you see it? What is the norm of the derivative? It's a scalar. Nicely. This is the square root of, well, first of all, what is the derivative? It is negative sine t cos t 1. So the norm of r prime of t is going to equal the square root of negative sine t squared plus cos t squared plus 1, which is the square root of 1 plus 1, which is the square root of 2. That's good. What that says is ds is the norm of r prime of t times dt, which is root 2 dt. So it didn't add any complications to our line integral. What that says is the line integral c of our function y sine z ds is now equal to, what's our bounds? They were so nice they gave them to us. This is the integral from 0 to 2 pi. One revolution of the circle, but then z went up. What is that going to give me? That's going to give me f of r of t, which is going to give me y was sine t, times sine of z, which is t. Another one. And then I'm going to get root 2 dt. Oh, and this takes us back. What is this? This is equal to the integral from 0 to 2 pi of sine squared t root 2 dt, which is a trigonometric integral of the 4th kind, where I have only even powers of sine and cosine. Cos is not even there, so I'm going to use the trigonometric identity. Sine squared is 1/2 1 minus cos 2 theta, and we're going to get at this guy. This is equal to root 2 over 2, the integral from 0 to 2 pi of 1 minus cos 2t dt, using a trigonometric identity. And this is equal to root 2 over 2 t minus 1/2 sine 2t evaluated from 0 to 2 pi. This is straight out because sine of any of those values is going to be 0. and this is going to give me the 2 will cancel, root 2 pi. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch of others. I'll see you next time.